Also, when you guys turn on my videos, are they hella loud compared to everyone else's? Is it okay? You just turn it down? Okay, I alarmed myself in my office one day. Okay, so we're doing neural control of human movement, which is dope because I love the nervous system. So if I'm a little more excited today, just wait till we get to cardiovascular. It'll be really bad then. Not again. All right. Well, at least my pointer works. Okay. So the whole theme of these two lectures is that complex, learned movements require precise, coordinated neuromuscular patterns and movements, not simply strength. So I know we have a lot of athletes in the room, so this probably doesn't need beleaguering, but I'll beleaguer it anyway. So here we have my boy, Austin Matthews. Actually, my boy is Morgan Riley, but anyway, Austin Matthews doing a slap shot. So if anyone would probably tell Austin Matthews to get a better slap shot. I don't even know if does he have a good slap shot? Harlan, does he have a good slap shot? Are you a Leaf fan? You're probably not, eh? Is anyone? BC, right. Is he famous for a slap shot? No. He's good. Famous for sniping. Okay, so we would not just tell him to go like pump iron. I'm so cool. We would not tell him to just pump iron, right? We know that it takes a lot. There's a lot of hockey players in the room. It takes a lot to get a good slap shot, a good wrist shot. Likewise, I had to write this down. Kia Nurse, the only WNBA player I know, because her brother plays in the NHL, right? Or yeah, for Team Canada. So she's doing a free throw. Once again, if she wanted to get better, you wouldn't just send her to the gym and tell her to do a bunch of whatever these are. Likewise, Serena Williams, about to serve. I have tried serving in tennis. I suck. I'm good at, well, not good. I'm okay at everything else, but the serve, I really am terrible. And like she's got a great serve, but obviously then there's a lot of other tennis players who probably don't have the same sheer strength that she does that also have great serves. So the idea is you need to optimize a lot of systems in order to get good at these complex tasks that require, I mean a lot of the time, years of practice in order to get good at them. So, what we're gonna do is something really fun. Hopefully you guys are sitting next to people you like, even if you're not, I don't care. Break into groups of whatever size you want. I prefer you just turn around, but anyway, whatever, if you want to walk around you can. So we're going to take 5 minutes, and you guys are going to talk about what bodily systems, and by bodily systems I mean anything. You can give me organs, you can give me, I don't know, kinds of nerves. Hint, hint. You can give me like anything, any kind of bodily system or thing on your body that needs to be functionally optimized, functioning optimally, in order to perform a complex learned movement properly. So what differentiates the best, or what needs to get integrated together in order to do something properly? Is everyone confused, or does everyone have a decent idea of what I'm looking for? There's kind of no wrong answers here. Get into groups, discuss, and in 5 minutes I'll get some volunteers to tell me what you think. Don't get ahead of your slide. You see those slides are open.
Brain, heart, lung. I'm running graphic vision and hearing.
You guys want another minute, or are you guys good? Okay. So one of the lovely grad students is going to write these up on the board. And just to penalize you for sneaking ahead to the next slide, not that I know who did, but someone who was sitting in the front, I can see their screen, so sorry, I just looked at them. You guys have to give me the sport that you're thinking about, and give me an example in that sport. Yeah, just so I'm cruel. I don't know why. Okay, so who has got something? What kind of a bodily system, organ, whatever? You can shout them out. Dan is a past writer. Or you can put up your hand. Go.
Respiratory system for swimming.
Beautiful. Yeah. Anyone else? We've got respiratory, This is gonna go slow. Wait, we can just keep on yelling them out. She'll write faster. What do we got? Yeah.
Like vision could be useful for like a tennis serve or something like that.
Perfect. If a bird flies in front of you right before you're about to hit the ball, that's problematic. Yeah. What else? Also, if you like throw the ball up in the air and there's a little bit of wind and it starts drifting the ball and you gotta catch it. How else could you detect wind? Yeah. So like skin sensation. What about the hockey players? When you take a slap shot, what kinds of things is your body feeling for?
Muscle.
Yeah. Oh, yeah.
Muscle.
Who said that? Yeah. Proprioception, that kind of thing. Perfect. Yeah.
Also like vestibular, like for your balance.
Perfect. Very fun to take a slap shot as you fall down. Which I know. Anyone else? You look so close to saying something. All right, I won't call anyone out. Okay, good job. So we're gonna do another group activity later on, so you're not put off the hook yet. All right, so within the muscle, so we were kind of talking more about like feedback and stuff like that. So we'll get to the second column there. So sensory feedback we covered, somatosensory feedback. So where are you in space? Any kind of changes in balance? Somebody, if you're in a contact sport, hits you at the last minute. Maybe you're doing a free throw. How, with your skin again, how sweaty your palms are. I don't know. I don't think that's well, but anyway. So these are all things that you will be kind of consciously aware of, your visual feedback. So we mentioned balance, so cerebellar activation. We need to have, once you incorporate all of that sensory information, then you need to integrate it centrally and create the proper outflow. So somebody hits you and you're falling off balance. All my examples are going to be hockey, guys, sorry. Somebody hits you, you fall off balance a little bit. If you're still going to take that shot, how are you going to adjust the shot? Now, how are you going to adjust your balance? How are you going to adjust your stance? So you need to be able to properly integrate all of that. The whole time you're doing that and sort of integrating some of that consciously. Some of it you're making decisions that you're, again, not really aware of because in theory you're such a finely tuned athlete that these things are happening automatically. You don't have to think about adjusting your balance. Some of these are happening completely autonomically, so changes in your sympathetic nervous system. So there's some really cool stuff in here about heart rate. Have you guys heard of those, let's say like alpine sport where you shoot and they shoot in between their heartbeats? What's it?
Biathlon.
Oh yeah, biathlon. Jerry Seinfeld has a good bit about them being alpine snipers, which I was, but anyway, so yeah, like the alpine snipers who are sitting there and, you know, breathing, getting their heart rate, oh, we talked about this in our lab, and then shooting in between heartbeats so that they don't get thrown off. Anyway, so you need to be incorporating your autonomic nervous system are doing this automatically. Sometimes you try to make yourself aware of that. There's a really cool area of research of people who are aware of their own heartbeat, and people who have done MRI studies on those people. Muscle coordination, obviously this is sort of more as you're learning a task and becoming better at a task. So the first time you do a slap shot, you're probably terrible. If, like me, your leg was broken the year that your team all learned how to do slap shots and you came in, no one was teaching you anymore, then you probably still have a bad slap shot, which I do. But muscle coordination is something that you're really learning those steps, and you're thinking about them consciously, but eventually they're happening automatically. And then, of course, adjusting or improving your strength, rate of activation, and power as you get more practice, and then you can sort of develop the pathways with your training. Okay, so basically these are all the things we're going to talk about today. Today and tomorrow, what's today? Thursday? Tuesday. I should have flipped this around. I did these as they popped into my head. But we're actually going to talk mostly about this stuff today, and then tomorrow, Tuesday, we're going to talk about the muscle stuff. Also, you guys don't have class on Monday. Is everyone ready to vote? Oh, thank you for cheering the vote. Are you guys going to vote? You should vote. I lived in the U.S., and I'm not going to get political, but I lived in the U.S. in November of 2016, and people should vote. Okay. Again, I'm really sorry this is annoying. This will be less annoying than my voice getting scratchy. Okay, so nervous system. You guys have probably covered all of this in other classes. You take a physiology class, right? But there are two divisions of the human nervous system, central and peripheral. Brain and spinal cord, and then is the central nervous system and peripheral nervous system are nerves that transmit information to and from the CNS. I'm not personally a huge fan of these delineations because, as you'll see, there's a little bit of crossover, but anyway. Also, this is tiny, sorry about that. But this is basically what we talked about just now. So, central, I think it's pretty obvious, brain, spinal cord, and your integrative control centers, which are, to me, the most interesting part of everything. I presume someone's taught you the afferent, efferent, exit thing? Yeah? Efferent goes at. Efferent or efferent is the exit. So afferent, again, all of those sensory inputs that we are bringing in that need to get integrated centrally and then leave through efferent division. So, we go over to the peripheral nervous system, exit through the cranial nerves, which we're going to talk about, and then activating these sort of motor pathways. This is what we're going to talk about sort of right here on Tuesday. Autonomic we'll talk about briefly today because I don't want to spoil it. I want to save it for cardiovascular because it's exciting. And it's 4 lectures. We're going to have such a good time. Okay. So really brief, well, it's not really brief. There's like 4 slides on this, but thought we'd touch back on sort of neurons and the basics of synaptic transmission. So we're sort of like stepping out for 1 second just to do a background. This is a stupid question, but who loves action potentials? Anybody? I really like action potentials. Like, being serious, I did a presentation on them when I was an undergrad. I'm honestly pretty nerdy. You guys can I'm not like pretending to be like this. I actually get really excited. Anyway, so we're gonna do just a really brief primer on action potentials. A, because I love them, and B, because all of these pathways are contingent on action potentials and neurons talking to each other. And this is something that we look at a lot in research, is when you're trying to potentiate different pathways, what's happening in those synapses that might be making a pathway work more quickly or more slowly. And a lot of the time, we get new neurons and you think about new connections and stuff like that, but what if there's actual, like propagation at the level of a synapse and that kind of thing. I see I lost a lot of you there, but it's very exciting to me. Okay, so here's a neuron, a neuron. Cell body, terminals, yada yada. You guys are you cool with this? You're cool with this. Do you want me to go over it in more detail? No? Okay. So, there's a part called the trigger zone. That's amazing. Okay. So, obviously, the dendrites are up here at the top around the cell body. This is the receptive areas that can conduct electrical impulses to the cell body. So if you want to talk to this neuron, you're going to do it through the dendrites. And the dendrites are just out there listening and waiting for feedback. And then everything is going to summate at the level of the cell body, obviously. Here's where we've got the nucleus and all that jazz. So if we have enough to go in this trigger zone, the nerve fiber, this axon, will carry electrical impulses away from the neuron cell body. towards an effector organ. So in this case, on Tuesday, we're going to be talking about the neuromuscular junction, so onto a muscle. My jam, again, is sort of nerve to nerve, or neuron to neuron. Actually, it's really nerve to blood vessel, but whatever. So we go away from the cell body towards whatever the effector is going to be down here. Today we'll be talking about a lot of neuron to neuron. So the larger the diameter of the axon, the greater the speed of neurotransmission. Large myelinated nerve fibers. Who knows what myelin is? Yeah?
It's really fat.
Yeah. So I actually didn't put in the video about saltatory conduction because I thought we kind of got that, but if you guys want, there's a video. You're going to see I have 2 videos for you in a second. But there's a video, so you let me know if you want me to put it in next time. So yeah, large myelinated, exactly, nerve fibers, which helps things to move more quickly, will conduct impulses more rapidly than smaller or unmyelinated. But still, if you have the same size and one's myelinated and one's not, the myelinated is going to go faster because of saltatory conduction, which is another really fun thing. And oh yeah, because you guys are French, you know, saltatory, why it's salt, it's junk, right? So yeah, good stuff. Okay. I was going to say something here. Oh, this is actually another area that colleagues of mine and hopefully my lab are going to be looking at, which is the larger the diameter, the greater the speed. And the idea that this has to do with sort of outflow at the level of the synapse and like neurotransmitter release from the neuron. So this is sort of like emerging in the field. So you guys know about Henneman's size principle. Do you guys talk about that with Darren? No? Do you guys know about Henneman's size principle? Maybe I'm talking about Henneman's size principle tomorrow on Tuesday. Okay, anyway, so forget I said any of this. Anyway, that you might recruit larger sympathetic neurons under conditions of extreme stress. But that's really just a pitch from my own lab, so that's not in your test. Okay, and then a synapse, as we all know, is a contact point between the axon of one neuron and the dendrite of another. So these neurons are then able to talk to each other, and if you get an action potential traveling down this axon at the level of the synapse, you're going to get neurotransmitter release. Neurotransmitters will then bind to receptors on these dendrites. Again, that's all going to summate at the level of the cell body, and as we reach this trigger zone, the axon hillock, again, if you've got enough change in ions, then you'll get another action potential traveling down the second neuron. We're going to cover that all in a little more detail now. So we know that all cells have resting membrane potentials, and this reflects the electrical charge difference between the inside and the outside of the cells. So the resting membrane potential is negative between 40 to 70 millivolts, which means that the neuron is polarized. So a polarized neuron is something that has a charge, polarized anything is something that has a charge. So our neurons are sitting at a negative potential, which means that there's, again, more positive ions outside the cell than inside the cell. Sorry, I really stole my own thunder there. The magnitude of the resting membrane potential is determined by the permeability of the cell membrane, which again is selective for each neuron, so we can control when, have you guys learned about all of this action potential stuff in your neural classes? Yeah, we can control when the sodium goes, when the potassium goes, yada yada. And then, of course, the concentration differences, because everything's always going to flow down the concentration gradient. That's one of the nice things about physiology. Once you know things go down concentration gradients, that's basically it. That's all you really have to know. And negative feedback loops. That's my little cheat sheet for you guys. Okay, so we know sodium, potassium, and chlorine are present in the greatest concentrations and are the primary determinants of the resting membrane potential. Oh, here's a nice actually figure showing sodium at rest more outside than inside. Does anyone know what this means, the small n, big N? Any chemistry? Huh?
Millimolar?
Yeah, millimolar, nice. So it's a concentration. A tiny concentration because it's milli. Potassium, more in than out, but then again offset by the sodium, etc. Okay. So, I don't think this animates. No, it doesn't. Oh, it does animate a little bit. Okay, so again, I think this is fairly self-explanatory in the slide, but you have a closed channel that's not going to let sodium, for instance, through this channel until it's somehow triggered to open. So we have these channels that are only going to let the ions through when they're open. They can't just diffuse across the cell membrane. Do you know why they can't diffuse across the cell membrane? You remember they're like, did you guys say molecular biology? I feel like I asked you this last time too. So we've got the lipid, the hydrophobic part of the cell. I'm just looking good. Agree with me. Okay, so the ions move freely once they're open. Again, along the concentration gradients, but can't move when the channels are closed. And so at rest, all the sodium channels are closed and a few potassium channels are open. Which is why you get a negative resting membrane potential, because the potassium's trying to get out. Remember from, this is going to be annoying, sorry, the last slide, more potassium in than out. So the potassium is obviously like flowing out. The sodium wants to go in, but those channels are closed, so negative inside. Sorry. Okay, we just said that. Okay. So the idea here is that if we just left this like this, if the potassium continued to leave the cell and the sodium continued to enter the cell, the concentration gradients for both ions would decrease and you would lose. Basically, if you just left everything open all the time, you would just have, everything would equilibrate and you would get, a mix between the concentration gradients and the electrical potential, but you would lose some of your negative resting membrane potential. But handily, we have the ATPase. So remember from last day, ATPase, what is that doing? And we know what it's doing based on the name. The name tells you what it is. What's A's mean? Yeah, enzyme. So ATPase is doing what? You can yell. You can suggest quietly. Break it. Did someone say break ATPs or make ATPs? Break ATPs.
Break.
Yeah, break. That's what I thought you said. Yeah. So yeah, it's breaking across the ATPs. It's the enzymes degrading them, and so it's using. You can see here, it's using the ATP in order to keep this, because now we're pumping things against their concentration gradients. Again, everything. If you leave it to its own device, it wants. It's like me. I don't want to be in big crowds of people. I'm going to always move along my concentration gradient. I'm going to go home. I'm going to go to bed. That's all I want in life, really, is to go to bed. So think of me, I really want to go, but if you need to get me here, oh, this is a great, Harlan, this is going to link back to your student of the day. If you want to get me here, you have to give me energy in the form of coffee, exactly. And then I'm here, and I look way too excited to talk about neuro stuff. So similarly, if you want to get the resting membrane potential all juiced up, you need to use ATP. So one of the reasons when we're creating all of this ATP, and we were, I was talking a lot about that a few lectures ago, how important it is to create ATP. We all know that's the end goal of all of the energy that we're consuming, is to try to make ATP at the end. And one of the key places you need it is to restore this resting membrane potential, because without a resting membrane potential, the cells are not going to be able to, so they're not going to become polarized, they're not going to be able to depolarize, which is the action potential. Does that make sense? Okay. I also gave another quick talk yesterday, and I realized I give the thumbs up a ton, so I'm really trying to keep a lid on that today. I'm sorry if it annoys anybody. Okay, so lights, camera, action potential was the name of my trivia team when I was in grad school. I'm just showing how cool I am. So here we have time in milliseconds, and here's the voltage. So again, we're sitting here at this negative, so now we're in a neuron. We're sitting here at negative 70 millivolts. And we're hanging out, and we're waiting for something to come along. Again, maybe another neuron has released a neurotransmitter onto the dendrites, and the dendrites are causing depolarization of the cell body, yada, yada, yada. So all of this is happening, and basically we're sitting in the axon waiting for something to come down through the axon hillock, the trigger zone, or whatever it was called. Okay, so if we have small depolarizations here, these are failed initiations. So something caused a little bit of something to come in here, a little bit of something to come in here, but it wasn't enough to summate and get us past this threshold at minus 55. However, once we get enough summating, so again, if you're sitting there and you're a neuron, and like maybe like me, will bring me back to coffee, you give me, I was gonna tell you guys about my coffee bowl, but I already said it. Okay, so every morning when I first wake up, I have a coffee, and I call it my coffee hole. My friends all say that's disgusting, because like, it doesn't actually caffeinate me, it goes in my coffee hole, so I'm like neutral, like these failed initiations. But without that, I can't have my second coffee, which is like my threshold. Huh? It's also on video now. It's really embarrassing, my coffee. Anyway, whatever. I think it's physiologically sound. So again, you're sitting there waiting for enough neurons to have excitatory inputs, and enough inputs to, a summation of excitatory and a lack of inhibitory to finally get enough to add up here to get you above threshold. Then you get this depolarization, so the sodium channels open up, your sodium ions flow in, depolarization, then your potassium ions go out and your repolarization, and because a lot of these potassium channels will open up, and then you end up getting this super negative hyperpolarized state, and you get back to it with your ATPase. So now, so that you always don't have to listen to me talk and I can have some water, I have fun videos for you. So these are from the textbook website. So obviously they're not probably, I don't know, maybe they'll work on your PowerPoint. Did anyone try them? No, they don't work. So I think if you guys really want these links, they do work. Oh, great. Okay. Just not in the PowerPoint. I mean the PDF presumably. So try the PowerPoint. Oh, yes. Okay. Don't steal my thunder. Here we go.
This length of axon can be likened to a piece of fuse. The burning match under the axon represents an electrical event that generates an action potential. This event normally takes place at the axon hillock. Recall that to trigger an action potential, the electrical event must depolarize the axonal membrane beyond its threshold. That is, the membrane potential has to become positive enough to initiate the action potential, which is an all-or-nothing event. Once the membrane reaches that threshold, voltage-gated sodium channels open up, and sodium rushes in, as reflected in the upward deflection of the membrane potential. But how is the action potential propagated down the axon? Look at the area just ahead of where the action potential is just fired. It is becoming more depolarized. A millisecond later, the positive charge associated with the first action potential has spread to an adjacent region of the axon. This area reaches its threshold, and this segment of axon fires an action potential. The area of axon that fired an action potential a millisecond ago cannot become depolarized now. It is refractory because its sodium channels are inactivated. In this way, the action potential propagates in only one direction, like a fuse. Now, 2 milliseconds later, the positive charge spreads to the next adjacent region of the axon, and it reaches its threshold and fires an action potential. The region of axon that fired a millisecond ago cannot be depolarized. It is refractory. The area of the membrane that fired 2 milliseconds ago has now returned to its resting potential, but it is too far away to be influenced by the current action potential. In this way, the action potential migrates, like the fire on a fuse, toward the axon terminal, where it is delivered to another neuron. Now let's watch the whole process at high speed.
Okay, I have one more, different voice. Does anyone have any questions about that stimulating little video? I really like the flame.
This ideal neuron, enclosed by a lipid bilayer, illustrates how we can flip the membrane potential by changing its ionic permeability. Ionic permeability changes when ion channels through the membrane open and close. This helps explain the phases of a neuron's action potential. At present, potassium is more concentrated inside the cell and sodium is more concentrated outside. The lipid membrane contains several closed sodium channels and 2 open potassium channels. As a consequence, potassium conductance exceeds sodium conductance. Free potassium movement across the membrane allows potassium to reach its equilibrium potential and establishes the cell's membrane potential at negative 80 millivolts. This represents the resting membrane potential. When the sodium channels are suddenly opened, sodium ions rush into the cell. At this point, sodium conductance exceeds potassium conductance. Accordingly, the membrane potential becomes more positive as it approaches the equilibrium potential for sodium. This change represents the rising phase of the action potential. Now, when we close the sodium channels, the positive charge that is accumulated inside the cell provides the driving force to push potassium ions out through their open channel. Now, potassium conductance exceeds sodium conductance. Potassium efflux takes the membrane potential back toward the equilibrium potential for potassium. This represents the falling phase of the action potential. Finally, the resting state is restored. Potassium conductance is greater than sodium conductance, and the membrane potential equals the potassium equilibrium potential.
All right. That was pretty good. I think they explained it a lot better than I did. Any questions? Cool. More of those videos, right? Okay. Oh yeah, so I just put the slide in. I know I already showed you this just to get us back. So, we're cool with neurons, talking to neurons, and all those pathways and stuff like that. So now we're going to talk about, again, the nervous system. Two divisions of the human nervous system, central and peripheral. We're going to start on the central here. Okay, so we'll start with the brain. So again, I presume that everybody knows this, but you've got your cerebral cortex. This actually was my jam for like a few sweet months in my master's, where we can use MRI to look at cortical activation patterns. Yeah, so if anyone ever wants to talk about MRI stuff, actually I think I have an MRI figure later on here. But that's how we study kind of what's going on in the cerebral cortex. That's really actually interesting in the cardiovascular physiology because it's sort of like a newer area of how the cortex controls that. But this is extremely important when it comes to motor control because there's a specific part of the cortex that controls motor control. Your motor cortex. Okay. Oh God, it's right there. Okay, so you have got motor cortex, motor control and voluntary movement. So yeah, you don't really, so diencephalon, we can, in your hypothalamus control body temperature. As I think we mentioned, this is important in a lot of sports. This is one of the things that's getting taken into account as you're going to be executing your movements. Brainstem, this is where you do a lot of metabolic function, cardiorespiratory control, but really it's like an integration zone. Because as you can imagine, everything that comes in to the cerebral cortex or leaves the cerebral cortex, and likewise with the cerebellum, is going to have to go through the brainstem, especially the medulla here, before it gets out. So this is really a place where everything, I mean, again, I think back in cardiovascular, where all of this, Yasmin's smiling smugly because she just did a presentation on this. Maybe you can do your presentation for that. Okay. But basically, this is where everything is going to get integrated before it goes down to the body. It's sort of the last site. So you've done all of your planning for a movement. Your cerebral cortex says, all right, you're going to throw this ball. And your eye says, oh God, watch out, there's a bird. And then your skin's like, oh, there's a little bit of a wind. Maybe somebody hits you, people hit you. I'm trying to use a different sport. So this is going to be the last site where all of that information can get integrated together before it heads out to actually reach your muscles and make sure you don't ding that bird. Cerebellum, coordinating and monitoring the complex movements and the incorporation of all of this feedback, which has connections everywhere. Questions? I'm trying to power through the anatomy stuff as much as I can because it's kind of less interesting than the functional stuff. Okay, spinal cord. Again, this is probably pretty basic for you guys, but the bones, the vertebral column, encase and protect the spinal cord. And the spinal cord is a major conduit for two-way transmission of information. So again, everything that you're feeling needs to go up to the brain, and everything that you decide to do, whether autonomically or consciously, has to get out of the brain or the brainstem or both. So this is obviously your main conduit for this. Spinal nerves exit through small openings. So obviously to get to the hand, you have to make your way. The vertebral column is built to protect the spinal cord, but things need to get out. so they exit through small opening between the vertebrae. And you've got spinal nerves that are going to connect to the spinal cord by dorsal and ventral root branches. Who can tell me the difference between dorsal and ventral? Someone's got to know. This is also French. Yeah? Yeah. Just go. I'll pretend you said
last
that.
year in anatomy we learned like in the door, out the vent kind of thing, like the.
Ooh, that's good. Actually, that's even better than what I was going to say. I never heard that. Yeah, so door is towards your back, and then ventral is towards your front. Door. What's back in French? Do, right? Isn't it? No? Is my French bad? It is great. Okay. Guys, don't leave me hanging like that. Come on. Okay. But that's really good. Yeah, in through the door. Stop it. I love it. Okay. Put that in your nose. Because that's actually going to come in really handy. Okay. This is going really well. So, yeah, I think my next slide is better here. Oh no, I have another picture. Why do I have this up here? It's hard with the lights. Okay, this is just another example. I think this shows the notches. Oh yeah, in the bone that are going to let the nerves come out. Okay, so if we cut a cross section, we have this sort of H-ish shaped core of gray matter. Gray matter is a collection of neuronal cell bodies. I learned for the first time that it's called gray matter because the first time people cut open a brain, it looked gray, and so they called it gray matter. That's fun. So yeah, so neuronal cell bodies, important part there. So I showed you that picture of the neuron at the beginning. This is really, not, well, it's what it looks like on a microscopic scale, but lots of times the bodies are very, very far away from the other ends of the neuron. Sorry. So you've got a whole bunch of cell bodies in the gray matter in that H-shaped core. Ventral and dorsal horns, which is obvious, so we're kind of facing the back here. And then the core will have three types of neurons: motor neurons, sensory neurons, and interneurons. So again, the efferents are the ones that are going out, trying to control whatever movement you're trying to do. The sensory neurons coming in, giving you all that intel. Again, obviously, like we're talking about visual feedback, that would happen in the brain, not here, but sensory feedback. So again, you feel a breeze, someone hits you, like in a sport. Someone like body checks you. And then interneurons are working in between all of these neurons. And I think I've got an example of an interneuron in a slide or two. Okay, and then we know the motor neurons are going to innervate skeletal muscle fibers, and these run through the ventral horn. Sensory neurons through the dorsal horn in the door. Really like it. I wish I knew that in school. Why did no one ever teach me that? Okay. And then white matter is the axons. So obviously you've got the cell bodies, the gray matter, they're all hanging out here. And then the white matter is all of their axons leaving. So you activate the cell body or you deactivate a cell body, and it's the axons that are going to carry that signal wherever you need it to go. If it's in your hand, your muscle, whatever. Good. Okay, so those were, that was the spinal cord. So ascending nerve tracts. We're going up, at the brain. So these forward sensory information from the peripheral receptors to the brain for processing, brainstem. 3 neurons will typically form the sensory pathway. So the dorsal root ganglion is going to contain the cell body of the sensory neuron, whose axon has relayed the information into the spinal cord. So you, I don't know why I always, maybe this is pain, it's more confusing, but I always thought about touching something hot for some reason. Maybe that's my neuro prof who told us this. But so the nerve endings are sitting inside your skin in your hand, but the cell body of that neuron is in my dorsal root ganglion. So that's obviously a really long axon. Really long, because my arms are so long. It's a long axon compared to the diagram I was showing you before. Okay, so that's sort of the first one here. So there is this little cell body there with that circle. The cell body of the second neuron will lie within the spinal cord itself. So again, here's the end of this neuron. So its sensory end is down this way. And then it's got its synapse, its terminal down here inside the gray matter. You can see in this example, it's actually synapsing onto an interneuron which is called an interneuron because it just goes in between two neurons. So the cell-bodied second neuron inside the spinal cord itself. And then it's going to go into the, I think this is another example with the interneuron in place. We don't necessarily need it here. And then that's going to pass up to the thalamus. And then the thalamus will contain, I think this example has like a fourth secret neuron, this interneuron here. The thalamus contains the cell body of the third neuron. So the thalamus, I was going to say, I wish I had a picture of the thalamus. The thalamus is your relay station. So I've lost my example. Touch something hot. One neuron sitting in cell body in my dorsal root ganglia sits there and it gets activated because of the heat. So that then, the second neuron gets activated. I think my ganglion would be about here. Is that right? So that activates the second neuron, which goes up to the thalamus. And then in the thalamus is a third neuron, which is sitting with its cell body inside the thalamus. The thalamus, here's a picture from an MRI. I used to have a picture of my brain from an MRI in my fridge. I would encourage all of you to get a picture of your own brains. If you want pictures of blood vessels, come volunteer in our lab and we'll give you pictures of your brachial artery, for instance. Okay, I digress. Here's the thalamus. It's a circular guy. It's actually a little bit obscured by that arrow, but it's a beautiful little circle in the middle of the brain there. The key is that it's in the middle of the brain. It's a huge relay station to go everywhere else. Good? Okay, great news. Group activity number 2. Okay, so now you're going to pick an action of choice, and this time, there's no cheat sheet afterwards. I don't know why, really, sorry. It's a really good idea to actually look ahead to your next slide. I didn't prohibit that. Okay, so you're going to pick an action of choice, and with your group, you're going to talk about specifically what sensory information is integrated. I know we kind of talked about this already, but frankly, I wanted to give you a break of me talking. So break into groups, and then we'll get maybe a few people to stand up and sort of walk us through the movement and what sensory information gets integrated. Bonus points if you pick something hockey related. Just kidding, you can pick whatever you want. Okay, go, 5 minutes. Sensory only.
I'm certified ramen.
Yeah, what is that? But it's not hot. Like ramen, I'd crave it more. You know what I mean? It's fucking sunny. It's gonna reach 17 degrees. But really? She's in the weather. Wait, what did you want? No, I'm down for food, and I just prefer like ramen and
Okay, what's our choice? Is this something cool? Punch in the face. Oh, I like that. Okay, sensory info. You gotta say the face. Like, you know.
Maybe you can be like
the puncher and the punchy.
Okay, do punchy on the face. Okay, I gotta like check why are you guys doing that? Let's hold it up, bro. Okay, you have to stand like for that's probably part of the drug.
stand up and present it as a group if you want to. Or one representative can stand up. Did anyone do basketball? Yeah. Give me someone from your group.
We talked about like